Okay, so what we're going to talk about today is life cycle of data. I think you probably think you know data. You don't know data. We'll talk about what I mean by that. But let's start with the AI news of the day, and I'm super happy to tell you something that's very, very local. Do you know about this? Only Cat? Anybody have an Only Cat at their home? So this is an AI company that's based here in Zurich. And it's so clever. This is the kind of thing that you could have done for a final project here and turned into a company. And so these two guys from here from Zurich, they didn't take my class, but I wish they would. They invented something that basically is a cat door, and it has a little camera on it, and it recognizes when the cat has a mouse or a bird or a frog or something like that, and then doesn't let them in, right? And so the cat very quickly learns that that's not okay. As they call it, I'll show you this little video here. I have to turn up the volume. This is, I think, the perfect
We can
AI
create a
application.
product which we saw that no one has done before, and we can help people solve this problem. So the product is an AI-equipped smart cat door with integrated prey detection. So whenever your cat comes back inside, we check its face, and we automatically see whether it carries prey or wants to bring you a gift. Which then triggers Flappy, or our cat door, to lock its door and prevent your cat from coming back inside. Only once we know that it is your cat and it has no prey, it is
Cat
allowed
face
to come
reco.
inside. You can connect to the cat door via app. You can always get insights, you can get funny images and videos, or you can get statistics from your cat flap. So we really want to deepen that connection between cat and cat owner.
Anyway, so these guys started up this company. There are a couple of competitors now, unbelievably. They make them here in Zurich. And remember when we did the lab that had you recognizing and classifying things in your hand? Same thing, right? They just did built a very clever little door, built a little camera, trained their classifier using an API like the Gemini or something, Vertex, and brilliant, just brilliant.
We can create a
Yeah. So want to tell you a little bit about an example that I ran across this past weekend about negative transfer. And this isn't a real product. So this is, when I was grading your assignments, I'm trying to leave a comment, right? And so I say, you need to give me edit access. So this is asking someone to give me edit access. This is permissions, right? Boom, boom, boom. I hit tab, what should happen? It goes to comment, sends the comment. Perfect. So I have been trained, like the cat, to hit tab and go, right? And that's the default action. However, if I'm asking to be an editor for that document, I say blah, 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 tab, it goes to cancel. It's the same product, right? It's Google Docs. And in one case, tab goes to comment. The other case, tab goes to cancel. That is a perfect example of negative transfer. So I cannot tell you the number of times I've had to retype my comment because of this stupid thing, right? This is a small example of the way the UX world works. There's one team that does this part and one team that does this part. Even though they have the same code base and the inheritance hierarchy of objects in the UI should be the same, it's not. So as a UX person, you have to think, how can I identify these problems and what can I do to fix them? The smart UX researcher will identify these problems ahead of time. Now you know about negative transfer, you will see these things in action. Better question for us for this class. I'll just leave this as a thought experiment. What negative transfers are we teaching our users in AI systems? So for example, just as a little instance to get your brain thinking, does this prompt do the same thing on this LLM as on that LLM? Sometimes yes, sometimes no, right? So we are basically building in non-compliance, non-conformance between different versions of AI systems that we build. Now that's cross-company, and so you can say, well, whatever. But this is within a company. Trust me, in Google Gemini, there's 8 different publicly available web UIs. They do not all give the same answer for the same prompt. Thank you very much. Okay, speaking of LLMs, there's a couple of things to say. First off, I read through all your comments I read through all your assignments, let me tell you, there are 100 of you in the class, roughly. Say it takes 15 minutes to grade an assignment. That's 100 times 100 times 15 minutes. You do the math, right? So, and I read through all of them, as you've probably seen. But one thing that I saw a lot of your comments was this is you speaking, I use an LLM to amplify on questions, to clarify concepts, to help understand in class. And I think that's awesome. Good job. However, one of the points of this class is we think beyond just the implementation of the particular app. One of the side effects that you might not have thought about is that I don't get the questions anymore. Poor teacher, right? But it's an interesting problem for me because I've lost a data stream. So I'm giving you this as an example of the larger social problem that we have, which is one thing to build an AI system, but you have to think about what the side effects and non-actions that are happening, right? So one of the things I've noticed is that fewer people come up to me after class and say, hey, Dan, what's going on with XYZ? I don't know what you're thinking. And I have not yet developed telepathy. I cannot read your mind. I'm trying. I do my best. But it's a data source that's lacking. So one of the things, so I'm not saying come ask me all the questions, but you might drop me an email saying, I didn't get this discussion about whatever, right? More generally, take away the notion that it's one of those things when you build your AI system, what are you also affecting, right? So when you build, for example, the world's best radiology cancer detector, what else happens? Do you descale an entire class category of radiologists? Think about those questions. Think about more than just the implementation. Okay, mainstream of today. This is where we're at. So everybody turned in assignment number 3. Aside from 4 people, you know who you are. You'll be getting a little note from me sometime soon. It's okay if you turn in late, but I need it. And what's really annoying as an instructor is I have to chase all of you down. I have to copy your email address and say, would you please send me assignment 3? Do it. Anyway, 97% of you, awesome, good job. I also will comment that assignment 3 is the hardest assignment to grade. So it will take more than 15 minutes per assignment. It's okay. Okay, so let's get into the topic for today, which is about data lifecycle. And I want to position this in the context of the history of AI, okay? So AI, the emphasis has really shifted over time. Once upon a time, we had rule-based expert systems. So the music you heard is from the same time that this system was being built. This is a system called Myson. In early 1970s, it was the epitome of AI. It was a rule-based expert system where they went out and talked to a lot of diagnosticians and said, how do you understand bacterial infections? What tests do you do, et cetera, et cetera. And so this is the kind of interface you had. Yeah, green on black, lovely. But you get the idea. You ask these questions, you go back and forth, you have a conversation with Myson. Incredibly brittle, right? But that's the way it was back then. And so people would build knowledge representations. They'd try to capture all of the domain knowledge of a field, in this case, bacterial infections in medicine. Then a little bit later, we started thinking about how to do machine learning, and we started emphasizing algorithms. And in particular, along with that came data, which is our focus today, building large models using some data set. The key thing I want you to take away today is that data is a human activity, and it has just as much to do with people as anything we're talking about. So it's one of these things you just think, well, data is data, isn't it? No, it's not just data. I'll tell you why. We then get into this phase of, we've got these complex machine learning models. How do we align their behavior, and how do we implement ethics in them? So today's class, we're going to talk about data. Even when data comes from humans, it's all based ultimately on human decisions. So doing data, it really is doing HCI. So this is central to our class today. So this, I have to keep doing this. If you're me and you're a user experience researcher for a large company, you do lots of different kinds of studies in order to generate data for decision making. So, for example, we do observational studies and experimental studies, right? Observational studies, we do in-lab studies. Come into my lab, let me show you this thing, right? And we'll test you. Maybe we'll hook you up to a pulse rate monitor or something. We also do field studies where we go out and watch people using our product in the real world. We also then do what's called behavioral log analysis, where you might come in or you might use one of my apps and it traces what you do, right? With consent, right? Full information and so on. So those are all observational studies. In experimental studies, we do control systems, we do lab studies, and we watch in detail what's happening. We also look at, for example, diary studies. Has anybody ever done a diary study? You know what that is? A diary study is where I ask you at the end of every interaction, at the end of the day, to fill out a little diary. I used your thing, and it was terrible. That's useful feedback. If you can say specifically what was terrible about it, it lied to me about the price. All that kind of stuff is really, really useful. Diary studies are a major, major pain. They're a pain to produce, and yet they provide some of the best data. One experimental data diary method is called experimental sampling method, or ESM, and it's where you sign up, and your phone will ping you a couple times a day, randomly, and it will ask you a question like, what information need do you have now? Or what's the latest app you've used, or something like that, some piece of data you want, and then you would write a little bit about that, and that accumulates into a diary. One study we did, we had 20,000 participants for a month. 20,000 times 4 pings a day times 30 days. That's a lot of free text data. Okay, so then you have to figure out, we're not going to talk about it, but you have to figure out how to deal with that kind of data. Critical incident studies where you watch how people use something. And one, for example, important thing when you're watching people use a system is how often do they hit undo? Undo is a signal that something went seriously wrong. Control Z, right? And then logs analysis, we will do experimental studies where we do A/B testing. And we'll talk about that in just a minute. So we've got this different space of stuff, of different kinds of studies that we as user experience researchers do. Now this is all, the studies we do, the data we collect, all this stuff is in service of trying to make our systems smarter and smarter. And ideally, I would like to have a wise system, right? I want it to be really super smart. And so in some ways, you think about data is the foundation for all this. And data then you aggregate into information. Information then gets put together into context, with context and experience to form knowledge. And knowledge then becomes wisdom. And T.S. Eliot has this great quote, which I want to give to you, famous poet. Where's the wisdom we have lost in knowledge, and where's the knowledge we have lost in information? So at each point, he's making this observation that this aggregation is necessarily a data reduction. When you aggregate stuff like that, something gets lost. So, and I love this cartoon because we have data, so there's individual data points, which we then identify, classify as information, we connect as knowledge, we have an insight, we realize this is the same as that, and wisdom is then making a path between them, right? This is a cartoon, this is not a deep philosophical discussion. But then, when people overfit data, you go crazy and you get a conspiracy theory. You've seen people do that, right? This is why Zurich and the pyramids at Giza are intimately connected because of some random data association. So don't go that way. Instead, what I would recommend, if you're interested in data science in general, I'd recommend this book. Came out, I think, last year, year before. Alfred Spector is my old boss. Peter Norvig is the co-host of this class, and he'll be talking in a couple of weeks. Chris Wiggins and Jeanette Wing, in particular, there is now at Columbia. She was at NSF for many years, and they came up with this whole data lifecycle story. So that's what we're talking about today. This is basically derived from that book, from the book outline, where we're going to talk about everything from generation all the way through use, and people, how they interact in all of those different phases. So let's talk about generation. So pre-existing data is obviously stuff that's out there on the web, so you can get it from wherever you crawl, you scrape, the usual story, right? However, as you know, all data is past tense, right? It discusses something that's happening. So you then build models to be able to make predictions and make a better picture of the future. The data that we're interested in, the human behavior, is created new by users. And they do things like they browse, they click, they move a scroll bar, they do all this stuff. For example, some shopping sites, like say Walmart or Amazon, maybe, just saying, they might very well track your mouse movements over the page, right? That's generating a constant data stream. Why would they do that? Because for something like 30% of all people, not you, but 30% of all normal people use the mouse as an indicator of what they're looking at. And when you look at the mouse track data, you could actually see this really well. And that's a measure of visual attention, right? If you're an Amazon or a Walmart or a Glaxus or whatever, you care about what people are looking at on the page. Because one of the things you want to watch out for is big sections of the page where nobody ever looks. If they never look, they never click. If they never click, you're wasting that space, right? So people will do a per pixel dollar count, per pixel price. And if nobody ever looks at those pixels, you're doing something wrong. So how do we do it? So that's one way of gathering data. So we have these browser plugins. There are things like CAPTCHAs which generate data. So you're clicking on all the boxes with cars in it. You're training their image recognizer. You may not know that, but they're leveraging your free work. There's things like Wikipedia or Wikimapia or Wikidictionary, all of these things, where people basically contribute data. So right now you can download Wikipedia for about 40 terabytes. Not that much. I can buy a drive like that for 100 francs kind of stuff. I will, just as a side comment, say, when I first started working in programming, I had a disk drive that was about this big, 3 megabytes. 3 megabytes. You don't know how good you've got. Just no idea. But what's happening is that people are creating, through things like Wikipedia or Wikidata, vast amounts of knowledge and vast amounts of information, basically what's called cognitive excess. I got some spare time, I'll go edit that Wikipedia article because there's an error on the internet, right? I'm gonna go fix it. You also know about crowdsourced data, companies like Amazon Turk, where you can go and ask people to answer questions. That's a whole topic in and of itself, because it used to be that Mechanical Turk was fairly diverse, and now, unfortunately, there are lots of bots that do Amazon tasks, and that doesn't help. So you can even ask to exclude bots from your Mechanical Turk studies, but it doesn't work. So there's a lot of crowdsourced data you can get like this. Also, large companies will have in-house staff. So Google, for example, has probably 10,000 raters, people that are basically the in-house Mechanical Turk. The advantage of having your own in-house Mechanical Turk is that you pay them, so they're motivated to do a good job. You can test them, which people do, and you can then dismiss them when their quality drops. And this is an inevitable thing. So if you hire somebody, you pay them a reasonable wage, and you have them on for a year, and you look at the quality of their work, it inevitably goes down over time. So you say, you need a vacation. So just go away for 3 months, go away for a quarter, come back, and the quality will go back up. But these people can then be trained. So you know their demographic information, you know their skill set, and the quality of the data you get from them is very high. But it's expensive. So all the large companies have their own in-house raters, who crowdsource people. There are also these things like data games, right, where you look at a galaxy and you can classify it as type 1, type 2, or type 3, using people to do that. And this is increasingly going away. But for a long time, there are these data games, and you can still imagine them. CAPTCHA, in fact, started as a data game and transformed itself over time into a way to verify humanity. Just as a side note. So that was done by Louis Van Ahn at CMU at the time. And I was at CMU last summer doing a AI project site review. And some graduate student had built the best final project ever. And it was literally a robot with an arm and a keyboard and a camera. And when a CAPTCHA would come up, it would then click and solve the CAPTCHA. So it was literally a robot solving the human detector. That was funny. Did just fine too, right? So, you know, you never know what's going to come out of a final project. We do experiments, obviously. We do lots of logs analysis. We have infinite numbers of sensors out in the world. So satellite imagery alone generates about 100 petabytes, you know, very, very quickly. We have things like OpenStreetMap, which is both crowdsourced plus generated sense data, right? There are projects like this Large Synoptic Survey Telescope generating 1,000 petabytes, you know, every year. So we have large amounts of data. But remember, key lesson, all data is a proxy. You might want to get that tattooed on your arm. You know, all data is proxy, right? You're not measuring often you're not measuring the thing you think you're measuring. If you're looking for visual attention, you can put somebody in an eye tracker, which I've done, and watch their eyes and see exactly what they're looking at on the page. But you don't actually know what their attention is. I've seen people, this is true, I put them in my eye tracker, and I watch them go to sleep. And it's like, what's the experimental protocol for waking somebody up? Or they're in there and they're looking all around at the page, and then I say, are you going to make a decision? I say, oh yeah, I was thinking about what I got to do tonight. But I'm getting eye tracking data. It's completely useless. So remember that eye track, even something as obvious and intimate and personalized as eye tracking data, is still a proxy. And then finally, we have the synthetic data or simulation category. In a couple of weeks, we'll have one of my colleagues, Andrea, speaking about using synthetic bots to create data of using systems. There's all kinds of trade-offs in that. When it works really, really well. When it doesn't work, you don't know it's not working, and you get crap data. So it's a trade-off. So I want you to spend just like a couple of minutes and imagine the task. Imagine this task. You're now my data scientist, and I say, how are you going to measure the success rate of your UZH students after the graduation? What data do you collect? Give you just a couple of minutes to talk about it, okay? And then, of course, I'm going to ask you questions. So what data are you guys going to collect?
I guess because it's like UZH students after graduation, I guess you're already wondering what they have to
Okay. Okay, my friends, what do you got for me? You are the chancellor of the university and you want to know that your students are happy and doing well. How would you measure that overall university training education effectiveness? What do you do? What's a data signal? Okay, back row, you're up. What are you going to say? You got something? I'm looking at you. Yeah.
We were wondering what you exactly mean with success, like only in the context of work or general?
Okay, that's a great question to ask. What do you mean by success, right? So what would be one definition of success?
How much money?
Income. That's great. Okay, next row. How about you guys? Got something? You got a data signal for me? Okay, what would you say? Unemployment rate. So he wants to know income. You want to know who's still got a job. That's another great one. How about third row? Oh, all right. What do you got?
We talked about kind of self fulfillment. So how happy do you rate yourself being?
And you get that by?
I think you would have to ask directly. Like,
Yeah,
I don't
a
think-
survey of some kind.
Yeah.
Okay, so you would send out a survey. So I guess all these questions are surveys. The unemployment case is hard because often they don't have a stable address and maybe not email, and it's tough, right? Anybody at this row? Anybody else? Yes, thank you. From the third row.
Yeah, we discussed that what they wanted to be and what they got.
Oh, was their expectation met?
Yes.
Okay, yeah. Okay, let's go with I'm gonna collect you guys all in one row. What do you got? Anything else?
We also discussed what success means.
Also, what does success mean? This is a great first observation. Before you measure something, you got to know what you're measuring, right? So, unbelievably, people don't do that sometimes. They'll go out and collect data. They don't know actually what they're measuring. In particular, I've told you before that setting up a survey is hard. Everybody thinks they can go to a Google form and create a survey and we're done. I've seen people set up a survey and ask questions where the people who get the survey have a different interpretation than the person who created the survey. And so you have to test your survey. Never deploy a survey without testing it. On the population, do not test it on your office mate. That's a waste of time. Because your office mate is, for all intents and purposes, a copy of you. That doesn't help. If you're going to look for unemployed Zurich graduates, you need to go find some and give them the survey, right? So it's not trivial to do this. Now, this is actually Peter's daughter. And they were out riding their bike on a road near home. And so this is not far from our house where we live. And this story is about where you get data from. Because they were out riding their bikes down this road, and Peter's chain fell off his bicycle. This has probably happened to you, right? So all of a sudden he did that. And so he fixes the bike, and you know what happens, right? You get grease all over your fingers, right? And so Peter noticed that a nearby pole is covered in grease. What's going on? What's your interpretation of this data? Any ideas? What's happened?
That this part of the path is very, the probability of your chain falling off in that part is very
Correct. There's a bump there. There's a big bump there, and you go bang, and the chain jumps off. It happens to me all the time. And so Peter, being a good data scientist, took a picture of this because this is a signal to the road crew. Maybe they go fix the bump, right? And how do you know it's actually reasonable data? Because you took a picture of the next pole, right? You see the point? Doesn't happen here. In a little bit, we're going to talk about counterfactuals. That's when things don't happen, right? So a counterfactual statement is something where the opposite is assumed to be correct. So for example, if a kangaroo had no tail, it would fall over. So the counterfactual is assuming something that's not true. That's important in data. So this is nothing happened here, right? So that's as much as signal as the grease-covered thing. And so this is the best XKCD cartoon ever. I used to think correlation implied causation. Then I took a statistics class, and now I don't. Sounds like the class helped. Well, maybe. Once you understand that cartoon, you are a data scientist. Right? So there's a lot to think about when you're looking at data. So this happened April 7th of last year, and this is a map of the US, and this is Airbnb occupancy rates, color-coded. Any idea what happened here? Why is that weird pattern there? I mean, this was in the US last year. Do you have an idea?
Solar eclipse.
Solar eclipse, exactly right. Give that man a point. This is the path of the solar eclipse on April 7th. I happen to be here, but that's a separate story. I was not at Airbnb, so I didn't contribute to the data. But sometimes you can see some remarkable correlations in your data set, right? So, or you look at something like this. You look at Google Trends over time. What are people searching for? And if you ask Google, over the past couple of years, how many people search in English for the words full moon? Guess what, right? So this is not causation, right? This is pure correlation because people look for it. The first time I saw this, I thought, that's crazy. And you can find all kinds of stuff like this. In particular, oh, the next slide is missing. Darn it. The next slide shows a search for the word kayak. And you see basically the same thing, where every summer you get this bump for kayaks, and never in the winter. But if you look in the US, you can see bump, bump, bump every June, boom, like that. And in Australia, every December, bump, 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 right? And so if you take the data globally, it's flat. So sometimes data segmentation, as long as you understand why you're segmenting, right? So let's talk about, once we've got data, what do we do with it? And I have taught entire classes just on the topic of cleaning. I'm going to give you 5 minutes. So it used to be that English used what's called the long S form, with that funny little, it looks like an F. And if you look at Google Books, and you do a search for a word like fave, F-A-V-E, you'll be surprised that fave, which is kind of a modern coinage, was really popular in the 16th century and 17th century. Like, what's up with that? And the reason is that the OCR mechanism for Google Books didn't know what a long S was, okay? So what you're seeing here, what all those things where it says, oh, not fave us, it's oh, save us. Right? So the orthography, the way people drew characters changed, right? So what you see is that if you look at something like fave, you get this incredible burst back here in the 1700s, and it's because of the misrecognition. So here's an interesting thing to think about. If you're relying on a data set from another company, suppose you're relying on the text of the Google Books corpus, you need to realize that that error happened, and you have to accommodate for it. Now, even better, you have to also know that the OCR guys at Google said, oh, wait a second, that's wrong. And so they fixed the OCR algorithm, and so if you go look for the word fave now, you don't get this. They fixed it up so that the data set now, this is now recognized as SAVE. If your data process is relying on that data set, everything just changed underneath you. This is the problem with not owning your own data set. Now, you're not going to own all of Google Books, right? You just can't. But you have to understand as an analyst that the data is not yours and it can change underneath you. It's, the thing about this data set is it's even truer now. But if you built in your analysis based on expectations of the way it was last year, things are different. You have to forever track that data set. So you get these, interesting things. Is this actually last, or is it SAST or lost? And so you get these. What's happening is that the frequency of these words changes over time as a consequence of the OCR. The OCR is quite good, actually. It even reads things in Fraktur, the font, and it gets it pretty close to right. But you have to realize the data set can change underneath you. Now, a moment about correlation and causation. So if you have a graph like this one on the left, those two plots, those two curves over time are obviously correlated. There's obviously a causal relationship between them. And we can build causal models where you can actually link different factors, different forces in the model and say that this makes sense because sales are driven by a combination of temperature, price, and a bunch of other factors, right? But this doesn't make any sense. So the whole business of causal modeling, which I'm not going to talk about, is based on figuring out what those models should be. And you want to figure it out because it's very tempting to look at data sets and say, oh, there's an obvious correlation here. And so this is one of my favorite ones. The number of math doctorates correlates with the amount of uranium stored at U.S. nuclear power plants, which is obviously there's no causal connection there, right? There's a whole website you can find. Do a Google search for spurious correlations, and you'll find a million of them. Like the amount of mayonnaise sold in the U.S. correlates with total energy production in the U.S. And all you're doing is seeing spurious correlations. Do not be fooled by them. So how do we not be fooled? We do experiments. So experiments can be obviously, we do data generation by experiment, and we take different groups of people and we give them different treatments, right? And so the way you want to think about this, the ideal way to think about this is you do an RCT, a randomized controlled trial, okay? What that means is that you've got randomized groups, right? For example, you pick people where you're balancing diversity, remember that from last time? We're trying to balance across all the things we think are important, all the factors we think will be influential in the analysis. So we have these control groups and treatments. We want to be clear about what the outcome is. What is it you're measuring? What is it you're measuring? Do you know that in fact that measure is a high quality proxy for the effect you're looking for? Do you have enough statistical power? This is not a class in statistics. Go take Chat's class this afternoon if you want to learn about that stuff. But you need to know these concepts. You need to have enough people in your data set to be able to see the effect you want. And how do you recruit? So obviously this is how you create your randomized groups. You might not think about this because when you do experiments and studies here, you don't have problems with people leaving your data set, right? So retention, how long you can keep people in, and attrition, which is how often people leave your data set, can be really, really important, right? Particularly if A, you're not tracking it, and B, if you're losing people out of your sample set who are in a particular population that you care about. We've had examples where we recruit a set of people, say a couple hundred people, and 20 people leave. You think, oh, that's 10%, I don't care. But you just lost all of the undergraduates, right? Because it's spring break. Right? So you have to know what's happening there. Often the ending criteria, the stopping criteria for the study, you don't know ahead of time. In some experimental settings like this, you run the study for a while and then you finally say, okay, we got enough data, we're good, our statistics are fine, let's stop, do that. Okay. Other studies, you actually want to know what the N is before you run it. but I've run a lot of studies like this where I didn't know how long I was going to run it. And in a couple cases, I've done studies where I set the thing up and it runs, and I thought I shut it down, and unbeknownst to me, it kept running. So this whole thing, this whole experimental framework keeps to collect data. And in at least one case, I set up a tracking system on somebody's, multiple people's laptops to track where they were searching. And I shut it down, but it didn't shut down. And it kept tracking for a couple months. And because we were trying to be, have private data, we kept all the data on their local laptop. And I didn't know this for a couple months until someone called me up and said, I'm running out of disk space. Is it something with your logging experiment? I'm like, oh. So I went and I found a bunch of data, which is great. And I ended up running it for 6 times longer than I had planned. And that data ended up changing everything I thought we were doing. Because there's a thing called the Hawthorne effect. The Hawthorne effect is when people's behavior is different when they know you're watching. I went and accidentally did not delete the logging software, and so they thought, oh, he's not watching anymore. I'm going to do a lot more porn, or whatever, right? Or a lot more shopping, whatever, right? And so what happens is that unacknowledged track ended up influencing our data interpretation. I thought I was doing a clean study, and turns out I wasn't. So sometimes you don't know when to stop. But there are these ethical requirements for stopping early. So if you find out, for example, that your experiment or the study you're doing is actually damaging people, for example, you've seen people end up spending more money on something because of an experimental study they were in, or not learning particular data, you have to stop that. So be ethical about that. One of the ways you do a randomized control trial is to do a pair matching, because you got groups A and B, say it's a cancer drug study. You want to try to match participants as closely as possible along whatever dimensions you care about. So for example, gender, age, health, basic level of health, and so on. And so you might try to find matched people. Somebody, A1 over here and B1 over here, both male, both in their early 20s, both very healthy. Subject number 2, you have a female who's in her late 60s. We're going to find a female in late 60s, put in group A, group B. That's if you're going to do a really high quality study. Let me tell you, it's really hard to do that. But if you're doing medical trials, you kind of got to. Right? You have to be aware of restrictions. Foreshadowing. We're going to talk about data model cards in the very end of the lecture. You have to track where your data is coming from and what it's being applied to. I will tell you from personal harsh experience how many times I've run a study, collected the data set, put it aside for 2 weeks, come back to analyze and go, who are the participants? I can't remember. So as a word to the wise, if you're ever going to do a study like this, include the metadata in the data file. I don't care how you do it, but make sure the metadata, who's in the study, how often it was run, the time, start time, end time, et cetera, all that stuff has to go into the data file. Do not think because it's in your notes you can remember where it is. You can't. I've lost more data than I want to think about. So make sure you record all that stuff. Ideally, the notion of a double blind is that people don't know what group they're in, and they don't know who's doing the study. And reversion, if there's a way to undo the study, this is not always true, but in a lot of online AI systems, you can actually back up and say, let's go back to an earlier version of this, when people revert the code. Okay, one more thing about this. Shoot, I was going to tell you a story about this. I'll remember it. I'll remember it later. Oh yeah, I remember it now. This is such a good story, I have to tell you. So this was from a couple, like 10 years ago or so. There was one group of experimenters, who were studying the effects of stress on mice. They did this study. They published a paper. Paper comes out, and another group, another university in the U.S. says, "Oh, that's great. We're studying the same thing. I'm going to replicate the experiment," which is great. You should do that. And so Group A's result were replicated by Group B, except they couldn't replicate the study. They had the same number of mice, same conditions, everything was the same, and they got a completely opposite result. It was like, we did this treatment, and Group A says it reduces stress. Group B did it, and it says it increases stress. Like, uh-oh. So, to their credit, Group A and Group B started talking together to try to figure out why they were getting different results. This is the way science is supposed to work, right? So Group A and Group B, they're working and they're trying to, is it the food, is it the water, is it the temperature, is it the lighting? And so they're removing all these different factors. They can't figure it out. They wasted a couple of years doing this. Pop, 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 pop. And finally, somebody said, "Oh, I noticed all your lab techs, Group A, I noticed all your lab techs are women. In Group B, they're all men." It's like, no, come on. There's no difference. And so they said, well, we're running out of ideas. What are we going to do? And so they switched the lab techs in Group A to be men, and all of a sudden the data switched. Okay, men are callous handlers of mice, or what is it? More studies ensue, and they finally figure out that it's the testosterone being exuded by the men lab techs that's causing the stress levels in the mice to go up. If they have all women lab techs, the mice aren't stressed out. Right? So, and they did this beautiful manipulation of the data, which was of the study, which was they ended up taking the T-shirts that were worn by the lab techs in Group B, shipping them over to Lab A, and using the women to run the studies, but they put the T-shirts in the lab space. Guess what? They duplicated the result. So sweaty T-shirts are bad. That's one thing. But the deeper story is that often factors will influence your results that you haven't thought about. In this case, they spent a couple years actually trying to figure out what was going on. After the fact, it's obvious. But I've been in lots of studies where before the fact, you get an effect and you have no idea what's going on. So let's try a bunch of stuff, and you end up, this is what research is all about. Now, back to HCI. So we do what's called A/B testing. It's another way of doing analysis. And the reality is you basically are setting this up for continuous improvement. And so the idea is you've got a bunch of participants, usually visitors to your website, and you do an A/B test. So option A, say, has a blue square in the upper right corner. Option B has a red square in the upper right corner. Then to see what the click-through rate is, or whatever your data you're analyzing is, retention rate, time on site, whatever. Okay? Which of those has a better outcome? And you might say, well, look, the red box does better by 24%. Okay? Awesome. Okay, now the reality is it's not that simple. You never do an A/B test. You're actually doing many, many more things. And so what people do is they set up what are called bandits. This is a one-armed bandit. And Peter took this picture in Las Vegas. It's a slot machine where you pull the gun to make it go around and make the choice, right? And so that's where the notion came from, because slot machines are called one-armed bandits. Get it? And so now when we run multiple options side by side by side, you get multi-armed bandits. And a bandit experiment like this is that the idea is each one is independent of the one next to it, right? So this one has no bearing on that. And so what the participant is doing in each of these cases is trying to behave optimally, and you're trying to measure all these different cases. So I forgot to put this in. There's a really great book that's about optimizing for A/B studies. And it's all about the mathematics of this and how to set this up. From a human perspective, all the different arms of the bandit don't know about each other. They're all running independently. That's the point, right? And, do I have a slide? No. And the thing you have to do, you as the experimenter, is to make sure that these things are really independent. And that's sometimes hard. And so what large companies do is they have a master experiment registry. So within the company, if, say, your group is launching the blue box, and your group is launching the red box, and your group is launching the yellow box, they need to know that they're not interfering with each other. And since a company like Google has about 10,000 experiments running at any time, you have to make sure that experiment 1 doesn't interfere with experiment 9,000. And that's sometimes hard. So you have to make all these different branches to make this happen. And what's so interesting about this is that one of the things you see a lot is people doing variations on the user interface. So here are 6 different buy now buttons. Now, which one of those works best? You can all design an A/B study for this, right? We can run 6 different arms and we can test this kind of thing. And the thing about it is that these small changes can sometimes be huge. So I meant to also put another slide here, but I've seen studies, and I've run these studies myself, where you do small variations on say, the UI design, and you get vast differences in performance. So one study we did is we moved a UI element in Google search across the page. The first arm was 0, second arm was 10 pixels, third arm was 20 pixels. You see where this is going. We just shifted over by 10 pixels at a time. And if you look at each position on the page, you get a curve like this. Like, what? That's for click-through rate. The ones in the middle are getting like 5 times the click-through rate as the ones on the far left. And the ones on the far right, forget it, 0, right? So position matters. And we thought this is just fantastic. But the interesting question is, is the marketplace level if I know that information and you, the buyer, doesn't? You don't know that? So this phrase, caveat emptor, means buyer beware, right? Does the buyer need protection from all these AI-assisted sellers? Is it fair when you're buying from Amazon and they've spent literally $100 million trying to figure out what thing is going to get you to click through on it? Right? Easy example. One of the studies, I didn't do it, a friend of mine did this. If you've got a purchase page on a web page, right? Amazon, all these places you could do it, it's all the same, right? Except one study said, well, let's add a coupon option at the bottom. Awesome, right? You get 10% off if you go to this website and download the coupon, et cetera, et cetera. Turns out very few sites do that because one of these studies showed that if people come and they get down to that point and they've spent a few hundred francs, they say, coupon? I didn't know I could find a coupon. They leave the site and go searching for a coupon, and some fraction of them never come back. You've lost customers. You don't want to do that. It's much better just to get rid of the coupon altogether, because you do not want to have participants leaving your study, or your purchase in this case, leaving your purchase web page in the middle of the transaction, right? So that's an example where the systems, the companies have much more knowledge because they've run all these studies. Let's do this one, then we'll take a quick break. Danny Kahneman won the Nobel Prize with Amos Tversky. Wrote this book a couple years ago, and he's talking about noise in the way people make decisions, right? And so if you think about it, if you do a sample, say, of shooting at a target, you can have a very non-biased, highly precise pattern like this. Excellent, you're a good shot. You can have a shooter which is biased, who's always pulling down to the left. And so every shot is a little bit biased off on one side. Or you can just have noisy, where things are all, the distribution between this and this is very different. But then you can have both of these. So you can have both biased and noisy. And so here on the bottom, we have these shots are both down, biased to the left, but they're also noisy within that bias. Now, I'm talking here about statistical bias, right? This is not the bias we were talking about earlier about human bias. This is just noise in the, bias in the system. Now, noise, as you know, is this sort of statistical perturbation around the target. An insurance company basically is making bets all the time. So you buy a package of an insurance policy from them to protect your car, say, right? And then when something goes wrong, you call up the insurance company and say, hey, my car was just run into, back-ended by somebody. And so the insurance agent will then write out, the check for it, right? The insurance agent assesses the damage and makes a judgment saying you get, 1,000 francs or whatever. If you're an insurance executive, your motivation here is to make the payouts small as possible, but also as consistent as possible, because I don't want this insurance agent giving me 5,000 francs and this one giving me 500 francs. I feel bad about you, right? I feel bad about the company because it's inconsistent. So, in this book, Danny Kahneman talks about going and talking to the insurance company and asking them, how consistent are the measurements that your agents are making? Good question, right? What you want is arbitrarily high consistency. So the same damage gets the same payout across all. And a company may have tens of thousands of agents, right? So, thing number one, the executives never ask this question. Even though it's important, they spent a lot of money training their agents to make the same assessment of the same damage. But they never actually did the study. And so when Kahneman said, how consistent are your agents? They said, well, I don't know, but I think it's between 5 and 10%. So he says 1,000 francs, you say 1,100 francs. But it's close enough, right? Great. Kahneman suggested that they run the study, and they ran the study. What do you think the answer was? How consistent are the judgments across agents? Any guesses? They varied by 50%. So somebody would say, this is 500 franc damage. Another person would say, oh, it's only 250, right? So you had this enormous variation, and they had no idea, absolutely no idea. And so there's bias effects within the insurance agency where, for example, people with older cars tend to get a lower judgment. That's a bias against older cars. And then there's noise. Individual agents making choices up and down depending on what they individually think. And so these people did not have a notion of what the noise versus the bias was. Okay, I'm going to stop there for 5 minutes. So let's come back together at 9:05, okay?
And I was like, this is good motivation. Like, maybe I'll do this for myself. But I just do like for my team and my project. And I was like, oh yeah, you could just do that instead of like reading papers and doing all the annoying linguistic shit. And I was like, okay, cool. So now I'm doing that. Yeah. So not working in job situations. I mean, I have also not worked in HR right now. Just writing that just says this is it. I mean, yes, that is. But like, it's gathering the data, it's doing the things I want to do, it's just making this up, and it's export it. It's not like, it doesn't think. Yeah.
all the stuff.
Are you also singing?
Perfect, yes.
26?
I'm not
Let me
gonna.
note it down.
I already pointed this.
Yes.
Do you want to do karaoke?
Yes. Okay.
Are you free?
I mean, probably. I don't think I know my schedule that far in advance.
I'll tell you that later.
But your birthday's on the 20th.
Yeah, but my birthday is on Monday.
That's fair. We don't work, like, go straight to this lecture. No, we go from this lecture straight to karaoke.
No. You've got that backwards.
It's like you go to karaoke, then you sleep. And then
Oh,
you
right,
wake up
lecture's
in the
on
morning.
Tuesday.
Yeah.
I'm sorry.
Uh-oh, I'm in big trouble.
That's Monday.
Even though that's not true for me, I just accepted it.
Oh my god, I have uni friends that I hang out with on here.
Achievement ticked.
I have failed to do that for the last like 6 years of my life. Yeah. Really? Oh, that's so sweet.
And nobody has to sing out.
They will not sing, I can tell you that.
It's fine.
But they will sit in the corner, look blankly, and be great.
Yeah. They must sing uncomfortably, I guess very badly. Not uncomfortably, but badly.
Well, I'm not ready for a phantom joke, but yeah, you're right. Oh, I will defend what you all with you guys.
What do you sing?
Yeah, I was gonna say you're like.
That's okay. But I cannot go high enough for him.
Perfect, we'll just go put out the start and then let me just keep up.
Yeah. And I'll take it. I will not sing.
I actually had to sing
Angel of music.
Like even the fact that I now have like student like
That's an insane song to sing in class.
Yeah, we had someone that could hit like
I
this.
add a lot more
She's now studying
into the
I think. I don't know.
because now I
I did other fans of the opera and also looked up, but not
So
the
my issue is, whatever.
You're probably not going to be available because there's already a city.
I was actually say I will call them and ask what the like what it's thing that we really do want to talk to her. It's actually the
What place is this?
it's like this.
No, I've never been to
They offer and I propose that they can turn every occasion into a spicy experience. Yeah, it looks like a place that has books. Also, yeah, it also sounds that's fine. Just give on this.
I know Ross, but also
That's exactly a lot of Wait, this is not how I normally sing, that's just how I sing that song. For having faith in I have to sing it as if every word
I have a quick question for you before we get to 905. When I teach this class at Stanford, no breaks. But everybody here seems to want a break. So is it standard practice at the university here to give a 5-minute break in the middle? Or is it just that Stanford students have bigger bladders? Okay, so we'll continue. It's just it's always kind of weird to sort of just stop in the middle. But let's keep going. I also realize I'm about a third of the way through the slides, and we only have 40 minutes left. Too many stories. So let's talk about this. So the optimizer's curse is the observation, the statistical observation, that the expectation of the maximum is not the same as the maximum of the expectations. And there's a really, if you're interested in this topic, there's a paper here, the optimizers course, I recommend to you. Here's the gestalt of it. We do studies, and for example, we'll do an A/B study, just like you saw with the multi-arm bandit, and we'll run different launches of different kinds of UI treatments. And one UI treatment clearly stands out, and it's predicted by the sample to give us, say, 1.5% improvement. In search terms, that's huge, right? So we go ahead and say, that's great, Mr. PM, you've done a good job. Let's go ahead and launch it. We launch it, and we actually measure what happens, and we get 0.75. And so you think, wait a second, what happened? Well, what happened is that there's this huge body of people that you never tested against. And so what's happened in your study sample is you've gotten a great performance. You've got this nice curve right here, beautiful, but then it gets washed away by all the other people in the rest of the non-sampled set. And so it drops down. This happens every single time. Every single time. Your model says it should do this, and you end up with 75% of that. So it's just one of those things you have to plan for when you're doing your studies. Okay, let's take another case study. Colonoscopy is a procedure you get done when you're a little older. And it's not the most pleasant thing in the world, but it's one of those things where we want to understand how much effort should we put into recommending colonoscopy for people. So there's a randomized controlled trial with over 50,000 patients. Link, you can go see it. So there are two groups here. Either the doctor recommends one, colonoscopy, or not. And the dependent outcome is what's the survival rate and how's the outcome post-colonoscopy, right? Now, here's the trick. Notice what this paper says. The treatment was, doctor recommends it or does not recommend it, okay? So here's what happens. The treatment group gets an 18% reduction in colon cancer and no reduction in death. And if you're a doctor, you think, really? Really? So these are the people who were referred to have a colonoscopy. So what happened here? It's kind of a pain, literally and figuratively and monetarily. But, and here's the but you have to know, only 42% of people in the treatment group actually got the colonoscopy. Okay? So roughly half the group was recommended to get a colonoscopy. Of that group, only 42% got it. Okay? Now, let's look at the stats for that group. Of those people who had a colonoscopy, 31% reduction in cancer, 50% reduction in death. Awesome, right? Wait a second. This group is no longer randomized, right? So 42% of people who had a recommendation actually got the colonoscopy. And so the other 60% roughly, 58%, might have said, oh, I feel fine, I'm not going to get it. It's kind of a hassle, I'm not going to just bother with it. But the 42% who did get the treatment might have said, things are not feeling right down there. I'm going to go get the colonoscopy, right? So it's definitely non-random. So the question for you, data analysts, what do you think the real effectiveness rate is? I don't know the answer. I don't think you do either. It's going to be somewhere between those two numbers. That's all we know. And so we'd have to do more trials and more, try to figure out how random that subset was to see whether or not that thing. So what do you recommend? What do you recommend? Should you get a colonoscopy or not? Well, probably you would say, well, if you're a doctor, you'd say, well, sure, go get a colonoscopy. But if it's coming out of your pocket, you may not think the same thing. Comment.
But I'm like a question of this colonoscopy, not just imaging?
It's very invasive.
Yeah, because I know, but it is for imaging. So
Usually when you get a colonoscopy, they also do treatment at the same time.
okay.
So they will take out little polyps and things. Yeah. So it's hard to know the value of a screening test. So it's called a screening test, but the reality is they also do a procedure. Yeah. Especially when the majority of people did not have it done. So make sure you understand this. There's also something we call natural experiments. A natural experiment is when something changes in the world that you hadn't planned for, you didn't cause, and you get an observational data off of that. So here, for example, there's some variable about income, and we have some policy effect here. So the government did something. I didn't do it. But the government suddenly said, we're going to make this policy change, and you saw this sudden jump, this sudden break. And this is often what you'll see in natural experiments. How does this connect to AI? Think about that for a minute. So we see other kinds of natural experiments here. So what's the effect of taxation on cigarette consumption? And you can separate out California from other states in the United States, because California adds 25 cents on top of every package of cigarettes bought, which doesn't sound like a lot, but look what it did. It had a very profound effect. So when you get a natural experiment like this, milk it for all it's worth, because you don't get them every day. And often you'll get, for example, major changes that you could never do on your own as an experimenter. And you have to be a little careful, even when you've got super clear data like this. So here's a paper that's written in a British medical journal. Parachute used to prevent death and major trauma related to gravitational challenge, systematic review of randomized control styles. And the thing here is, the result is we were unable to identify any randomized controlled trials of parachute intervention because you don't want people jumping out of airplanes without parachutes, right? So you're not going to do that study. And I have to point out, this is a end of the year paper from British Medical Journal, so it's pretty humorous. And so then the next year, this paper comes out. Parachute used to prevent death and major trauma when jumping from aircraft, a randomized control trial. So they asked for it, we're going to give it to you. And the figure explains it all. Right? There were no traumas associated with leaving a plane without a parachute. Now that's just funny, but the point of this is, even for randomized controlled trials, you have to understand what those conditions are. That the conditions here are the funny part, right? So you have to understand them. So when you're collecting data, there's a bunch of guidelines here. Legal and ethical constraints. How much should you collect that data and how long should you retain it? So retention of your data becomes an important thing. It used to be, say 2000, retention of data was a big deal just because you ended up with petabytes of data. Now nobody cares about petabytes. You can just keep it all. But often companies will downsample it just to simplify further subsequent analysis. And do you keep all data? For example, when you've got these satellite passes, you could just sample the data, but you have to realize that sampling bias happens a lot and things change over time. Almost every data set at Google has metadata in it that says we changed the collection method here, right? So a data set, when you get longitudinal data, almost always comes with annotations saying that what changed during the course, especially if it was longer than a couple of months. So as an analyst, you have to understand how the data collected process changed and what that means for your interpretation. So if you don't have those annotations, you don't have a full picture of the data. We want to actively learn from the data we collect. So you don't want to just do a fishing expedition and collect absolutely every statistic possible. You may want to have a broad reach, but you don't want to collect absolutely everything. And you want to be able to match the collection process with how you're going to be using it. You have to be especially concerned about people and their data. So one thing to recognize is that data is an asset when you can collect it and analyze it. It can be a liability. This doesn't apply for anything you're going to do in the university, unless you're doing research studies. But you have to think about personally identifying information, so PII. And you have to balance for different groups, avoiding bias in the inferences you make. And it's really easy to get poorer quality data for less for smaller groups. Account for cognitive biases, which we talked a little bit about. And so there's this really wonderful study to tell you about. This is a Stanford study done near where I live. And what they did is that they got these fancy different kinds of mustard. Mustard with orange marmalade, oh, this is all jam, sorry. Orange marmalade, apples and cranberry, pear with honey, figs and black tea, fine. You have a dozen different kinds of jam. And you bring in people come into the grocery store and they sample the jams. And how do you like this one? How do you like this one? So on. You collect the data. Great. And one of the things these guys discovered is that the one that scored the highest was always the most recent one, this one, or statistically speaking. So you may have really liked fig, right? But in general, people will choose the last one, the one they had most recently. It's a very clear, well-known bias effect. That's why you do multiple runs and you randomize the sample order, right? And so lots of the online form survey creation stuff has this built-in capability to automatically randomize the order of presentation. So you see this kind of thing all the time. There's a bunch of them, a bunch of effects like this. Then there's problems with your sampling method. So this is an infamous ballot in the US from a few years ago, asking people to vote for president and vice president. And this is called the butterfly ballot because it opens up like a butterfly. And the problem, well, let me ask you, what's the problem with it? Potential problem with this? Anything? Do you have an idea?
Well, because sort of the person who is second is often is rather likely to not be perceived as having the second point. And Pat Buchanan, who's like a kind of far right whack job, received more votes in the county where this ballot was cast than anywhere else, despite like no particular strength there.
Right. So there's the primacy effect too. So the recency effect was the last thing. There's also a primacy effect. So Pat Buchanan is also the first guy over here, and Bush and Cheney were the first one over here. And as you know, this whole election was contested for all kinds of reasons. There's another problem. Another problem is that lots of people couldn't figure out which hole, because you took a stylus and you punched it like that to choose whatever. And so people would see this and then push that hole. And so it's just not great. Because if you didn't push the card in completely, it wouldn't align properly. So it's just fraught with errors. So this butterfly ballot was infamous because it just led to all kinds of issues. So the data collection process was faulty. Weather stations are also infamous for underreporting, overreporting, and sometimes you can figure out what the bias is and counteract the bias. But, birds sit on them every so often, right? So the little thing that goes around doesn't go around because there's a bird butt in the way, So what could go wrong? There could be birds on it, right? There's all kinds of things go wrong with that data. Okay, let's turn to data ethics. So we've collected data, we understand some conditions of that. So ethics around data, right, across all database systems, whether they're AI systems or not. The first one is probably privacy and who owns the data and how they maintain it. Tracking provenance, for example, is a big thing. Obviously, you want to have the data be as accurate as possible. So your job, looking at you, is as a user experience researcher in AI, is to make sure you have ownership and make sure it's accurate. Provenance is, where did the data come from, and you track that. In particular, as the data evolves over time. You may subsample the data set, you may blend in, you merge in other data. You have to track all that stuff. I will tell you from practical experience, this is a huge problem. Most big companies now have provenance tracking systems, so that when you have a data set, you can say, well, we did this, we excluded this, we transformed it this way, and you have to be able to track all that stuff. And ideally, be able to revert back to the original data or some point in between. So that's a big thing. You have to know what the intended uses are, because some data can't be used for certain purposes. Those are all legal restrictions. And you have to honor, who owns the stuff. And in some cases, you have to be able to track usage so you can pay royalties, right? I'm sorry to tell this to you as students, but it's this kind of stuff you're going to face when you have a job like this. So I guess a year and a half ago, the US passed this AI Bill of Rights, which basically says obviously true things. The problem with this and all AI legislation is implementing it, because often the data is ingested. So for example, training an LLM is often trained on these vast text data sets. And so there's one called lib4, which is really big, terabytes, petabytes of data. And the Atlantic Journal in the US published a tool that allows you to see if your data is in there. And so I just checked, just out of curiosity. My books are in there, and 59 of my articles are in there. Nobody asked me about it. And so the problem is, you can have all these protections and requirements, and if people ignore them, then you have to have an enforcement. And unclear how that's going to happen. So, for example, this thing here, people should be able to opt out of such systems where appropriate. I can't opt out. It's not an option for me. So I want to point out fundamental truth: data is a liability as well as an asset, right? Especially when you get sued, because if you've got a few exabytes of data, and some judge says, well, we need to see every record associated with this, that's a huge cost in and of itself, just accessing your own data. So there's a bunch of stuff that's happened in Europe, and there's the Swiss data protections, which is from a couple of years ago, but there's particular guardrails for handling data about employment and economy, all this kind of stuff where it involves personal data, tracking what people are doing. Because Switzerland is a small enough country, as we saw in the previous examples from yesterday, when you dissect down your cells to a small enough level, you can almost easily identify people, right? So it becomes a real problem. So there's a bunch of stuff that's going on here. As you've seen in other examples with, say, images, here's a bunch of data. Is this representative data? We have kind of bias effects here. And then, of course, so this is a presentation from a couple years ago, and this is the current one. There's a huge Indian bias here, which is really interesting to see. I also want to point out that data, as we collect it, is non-stationary. So most data is assumed to be independent and identical distributions, right? That's sort of the standard pressure and temperature of data. However, I will tell you, it's not true. So what you have to do as a data analyst, as a person who's considering building an AI system for humans to use, you need to understand what those biases are and counteract them and account for them. In particular, most real-world data changes with time. So you could have an effect like a stock market crash. You could have periodic changes like Black Friday sales. And you also have gradual changes. So these are all true simultaneously, right? So you can get adversarial changes where this is a bigger thing than you think. Spammers changing the market for ticket sales. Taylor Swift had a huge problem last year with this because people built bots that would go off and exclusively buy their tickets and then deprive people who lived in the area of the opportunity to get those tickets. So this sort of adversarial stuff happens almost everywhere. Anywhere there's a dollar to chase, there will be an adversary or there will be a spammer, right? So Google has for years had a problem with what's called search engine optimization, which are people who try to coerce the system into doing what they want, try to show your product at the top, and so they do all these crazy things to make that happen. For years, Google has had an anti-spamming team to counteract this. And so it's a constant game of spy versus spy, and that's why Google doesn't publish all of those guidelines, what they're doing to affect the ranking, because the spammers will instantly jump on that and then modify their behaviors, which modifies the data, right? You also get sampling changes. So for example, very non-random set of people may install cookie blockers. So if you're looking for cookies to track your data collection process, probably doesn't work. Interesting thing for you as an analyst is how do you discover that that kind of thing is happening? You have to look at a time series and start to understand when things start to drop off, why that drop off is happening. So part of your job is to stay up to date on the longitudinal data and see what's happening, try to explain it. Then you get these effects like weekend shifts. You cannot look at Google Trends data, for example, and not see where all the weekends are. If you look at almost any piece of data, you'll see this Saturday, Sunday, Saturday, Sunday, Saturday, Sunday, everything, right? And of course that shifts from country to country. It's not Saturday, Sunday, say in Israel. So you have to be able to be aware of all these different changes. And even so, you have to realize that there are all kinds of things that can happen. So there are simple models. As an assignment, you could write a model for this and be pretty accurate. Carrot's the same, right? And then you do something like the flu. Remember I mentioned to you the flu trends model, where Google built a model to predict the incidence of flu in the US, and it was highly accurate. And then those two guys left the company, and the model drifted, and all of a sudden it became inaccurate. So not only do you have to be longitudinal in your analysis of the data collected, but if you have a model for that data, you have to keep that up to date as well. Oh, here's the kayak. I'm just misplaced. That's kayak in the US, and that's kayak in Australia. So they're sort of in versions of each other. Okay, managing data. If you're in charge of collecting data to do analysis for HAI purposes, there's a bunch of things to think about. I just want to give you kind of the top level view of the peak. You need to think about how you partition and make access to the data. Again, this is probably not your concern, but you need to be aware of this. I've talked about metadata and provenance and the retention policies, and you've got all this different kind of stuff, right? And you have to be able to track back to the original source data anytime you make an interpretation of that data, right? So there's all kinds of things people do and to their data, and they may not even be aware of it. So there's filtering steps that happen. There are normalization things that happen, spell correction, standardization, summarization. One of the best examples of this I know is you have to understand how different systems code data. For instance, in Google Books, I was working in Google Books a couple years ago, and I thought, oh, wouldn't it be interesting to see the distribution of books by language? So Google Books has got 20 million books in it. How many are in English? How many are in German? How many are in whatever, right? So I did the obvious thing. And I was surprised to see that something like 50% of the books were in Norwegian. Norway is a great country, but come on. I don't believe that. And so I looked into it, and I was trying to figure out what happened. And so finally I talked to one of the data experts in the books group. I said, what's going on here? And so we looked into it. It turns out that there are several libraries that use a particular cataloging piece of software, right? And if they don't know the language of the book, or it's in the default language of the country, they put in no, N-O, into the field. Never use an abbreviation like N-O in place of a language code, because that's the language code for Norwegian, which is why 50% of the books were in Norwegian, okay? So that's a stupid error, but that happened not from any one person, but from a bunch of different libraries using the same cataloging software. Use null or something, right? Be better. But these kinds of things happen all the time. You have to understand this. And so in California, there's a guy, this is a true story, you can get a personalized license plate, right? And so he decided, I want the word null. Wouldn't that be fun? It worked up until the point he started getting traffic tickets sent to his house. He ended up with thousands of traffic tickets. Any guesses why? If they miswrote down the license plate, it defaults to null. So he ends up with all those traffic tickets. So it was difficult. Likewise, Popeye the Sailor Man lauds the use of spinach as a wonder food, right? And that was actually from the 30s, 1930s, when spinach was widely believed to be very high in vitamins and minerals and all that stuff. And truth, it's kind of only okay. But it was a mistake in the data analysis that's been propagated into the culture, right? And then, of course, there's this, which you might know about, this XKCD observation that historical records show that millions of business transactions occurred on December 30th, 1899. This economic activity sparked the digital age, culminating in a data festival on January 1st, 1970, when many early digital files were created. You might have seen this and wondered why. And it all is Unix's fault, right? And so there's a default date, and so things do that. And more recently in the US, as you probably heard, there was the claim by the Department of Government Security that people 150 years old were collecting millions of dollars in Social Security payments. And that's the default value for people who've died. They didn't know that. Huge mess. Data is important. And so what the practical thing people have been doing is building what are called data cards, which are basically disclosures of everything that the people who collected the data, created the data set, did to make that data set. So yesterday we looked at, really briefly, at the US Census from 1994, and the model card, the data card for that, gives a long explanation about how the sampling was done and all this stuff. If you create a data set, make a data card. Make sure they don't get separated. They have to go together. So a typical data set includes things like, who obviously the publisher was, where the funding came from. Where the funding came from, that's important. Also, sensitivities about the data. Things that are included, things that are excluded, things you have to know about, including shifts in sampling procedure. So if you get 10 years through this longitudinal data set and the sampling procedure changed, that needs to be in the data card. Okay? So part of your responsibility developing AI systems is when you're building data and training models on data sets, read the data card carefully. So as you probably know, data is not, there's no such thing as raw data. I've seen this happen many times where people assume that everything's correct, you just collect the data, we'll interpret it, we're done. But the fact is, everything has a kind of context built in. It has a default interpretation. So this can lead to data quality problems. And of course, if you're building your ML system, your AI system on that, it causes all kinds of problems in what we call a data cascade. So here's an important thing. Data quality, data collection process is really hard, important work. It's not just something you give to the cheapest intern. So in basic, I love this quote, machine learning is the high interest credit card of technical debt. So technical debt is when you leave things for later. So for example, software engineering often talks about the technical debt that you build into the system because you leave a comment saying, somebody in the future will write this code. No one here has done that, right? Right? That's technical debt. So this is technical debt for data. And you can finesse a data quality problem with hyperparameter hacking, but don't count on it. Don't count on that stuff. So the reality is we do the best we can, but data always has problems. And your only answer is to understand the issues and figure out how to accommodate them. So as an example, a couple of years ago, Google put out this big data set, which was short statements labeled with the sentiment. And the idea was that people could then use that data set to train their sentiment classifiers, right? This is a happy comment, this is a sad comment, whatever. And it turns out that, so Google did this, and it was unfortunately done by summer interns. And not long after it was posted, people discovered that something like a third of all the sentiments were actually wrong in the data set. So all the classifiers built on that data set are basically bogus. Okay? If the person who built that trained model didn't know that that was the data card, which was updated to say 30% of these are wrong, you're never going to debug it. You've lost the important information. Another one that happened, this was in 2006, AOL had a big search engine. They no longer have a search engine. They outsourced it to somebody else. But they decided that they would release a large search data set, 650,000 users, 20 million searches, pretty big data set. And I and everybody else in the search community, when this came out, said, oh, that's awesome, and immediately downloaded it. Okay. I have a copy of this. But 3 days later, they took it down because people, even though they had done best effort work at anonymizing the data, it was not enough. It was possible to actually figure out pretty easily who everybody was. And so there's a famous New York Times story about this. And so 2 employees were fired. The CTO, who's a friend of mine, was resigned. It was pretty straightforward to go from a user ID number to an individual, Thelma Arnold, who lived at this place and this address and so on. So it's pretty easy to do that. Bottom line, anonymization is really hard. It's really, really hard. And that is why Google never releases any data sets about search. There are solutions, there are ways to work around this, right? So one approach is to think about federated data analysis or building federated learning systems. And so you can do these things where you have analysis and build machine models based on these different data sets that are distributed. And what people want, obviously, is to be anonymous and to be able to delete their data. So you probably heard that 23andMe, the genetics company, is going bankrupt this week. Yeah. It's a long story. But anyway, if you have data on there, you might want to consider deleting it because all your data is going to go to somebody else and you don't know who it is. It's going to be sold to another company. So being able to do that is really important. At the same time, people want to participate, right? At the same time, people say delete and they say, oh, I didn't really mean it, right? So the user interface for this has got to be able to accommodate that. Remember, when people say delete, they don't always really mean delete. As you know, people will give it encryption keys and then they promptly forget the encryption key. And of course, they want to get the encryption key back, et cetera, et cetera, et cetera. So what I'm telling you is all this data stuff has a huge human side to it. I'm just going to touch on this really briefly. There's a method called homomorphic encryption, which allows you to use these distributed data sets. And the key to it is basically to encrypt the data and then give operations that will work on the encrypted data just as if it were the regular data. That's a whole nother class. But the cool thing that happened, it was developed a long time ago in the 70s. The theory, but it's a trillion-fold slowdown. And then in the 90s, 2009, somebody came up with a method to only reduce it to 1,000 times. And now every big data company has this. So the Oracles of the world, the Microsofts of the world, the Googles of the world have this as an option. So there is a way to encrypt data in a way that is privacy preserving, but it's expensive and it's slow. So your responsibilities as a data engineer are obviously to ensure data quality, right? Keep things private, allow people to have transparent access to it, make sure people understand what the policies are, all these things. It's important for you as a researcher, as a system developer, to get that stuff right. So here's a big thing. Problem first, data follows. I have multiple stories about this, but in one case, Google Street View, they were driving around and they said, hey, we got all kinds of data. We see all these Wi-Fi attachment points. We can collect data about the GPS location of every Wi-Fi point we drive past, which is basically the entire United States, almost. And so they just said, well, we don't know what we're going to use it for. We'll just collect the data. A couple years later, that was people discovered that had been done. Google was sued. $500 million later, it's been resolved. But that's a lot of money because somebody didn't have decent data practice. Don't just collect everything. Make sure you have a purpose for it. Of course, you want to make sure your data is well done, well documented, clean, and all that. You also have to monitor the collection method. How does that data get into your system? Come back to that. That's an important thing. I'm going to skip over this because I want to get to this. Data it comes in a pipeline. It's generated, there's a problem statement, you collect and label the data, you clean it, you do all this stuff. And at any one point in this process, errors that happen there can have effects later on. So for example, when you get the data collected, if you have a problem with that and you end up with a biased sample, it's going to influence the model deployment. So the actual use of it. So there's a contradiction here, which is, I'm going to skip over data security. I want to point this out. I'm going to come back to the cascade. There's lots of reasons that you, as the data scientist, person working to develop the data set for your model creation, should be paying attention to things like the Belmont report. Basically, you should understand that you're trying to collect the data to provide value to the community you're collecting it from, and not discriminate against them and not violate their privacy. You want to be able to do all this kind of stuff. So we create these data pipelines, which work, the kind of way you think, you collect the data, you train, so on. This is what you know about from your ML class. But the reality is that it's more complicated. So I love this illustration on the left because capturing is often really big and hard and complicated. And by the time it gets to the end, you're going to be subject to governance, to external regulations, both at state level and federal level. And so we have these problems where bias can creep in anywhere in the data cascade. So the data card, for example, records who funded the data collection. That's important. I've seen data sets where when I analyze the data, I think, oh man, this is incredible, wow, fabulous. And then I figure out who funded it. And I have to throw out the analysis because I realize there's an inherent bias in the way the data was collected. So, hint, read the data card first, right? You can save yourself a lot of trouble. So we have all these different aspects of data analysis. What the funding is, the motivation, the design, what the goals of the project were, and how that all gets out into the world. So obviously, I don't have to repeat this. Use a human-centered design process in all of this. Make sure you understand what your metrics are. And please, for heaven's sakes, look at the raw data. You cannot believe the number of times I've found problems because analysts didn't look at the raw data. It sounds like data science 101, but people don't look at the raw data, and you can. You now have been inoculated. And obviously test it. You cannot test your data enough. So we've got all these kinds of things that are important to getting the data right. And I want to end up on this last section here about ethics for data workers. I'm running out of time, so I'm going to roll over just a couple of minutes. My colleague Nithya wrote this really interesting paper a couple of years ago about how everybody in AI wants to do the model work. Don't you want to do the model work? Yes, you do. Nobody wants to spend time with data collection because it's boring, it's out in the field, and yet creating the data, doing collection, and labeling it is about 25 to 60% of the total operating expense of the ML project. So a lot of that data rests on the backs of humans that do it. So you have data collectors that are out in the field, and this is a study she did where she went out and interviewed a bunch of data collectors and looked at the raters who annotate that data, and then the researchers who end up using it. So you have collectors, annotators, users. So if you got developers here like Andrew Ng, we come back to that data cascade. So it's important to get the data right early in the cycle as possible, because almost everybody who has done any kind of serious ML AI system has had problems with their data. Almost everybody's had this problem. And so it's caused by these problems where the data is collected under conditions you may or may not understand. And so you need to have this downstream accountability. So the reality is most data collection is done somewhere else by people who are not paid enough in sweatshop conditions, and raters are part of that process. So the rater first design, this seems obvious, but people don't do it over and over again. You need to be able to design a UI for the raters that allows you to undo your decision, or it doesn't force you into a forced choice. So you want to allow the raters to be able to edit and change their ratings, right? So part of being a human-centered design is including the raters who are also humans. And so data collectors are the people on the front line out in the field, inserting thermometers into people's mouths and actually taking those numbers. And so what you find is that they're highly motivated, they're getting paid, but they may not understand what the ML people need at the end. They're so far from them in terms of the cascade that it's a long process. So for example, the last quote here is often the field collecting people would forget to reset their GPS app, and instead of recording it every 5 minutes, they would record over the base of an hour, which completely breaks the data integrity. So all of a sudden now you have to figure out how to reverse engineer that, and you can't. You have to go change the rating process. So before you go, here's the QR code. While you're doing that, let me finish up by saying the point of today's lecture, I think, was to illustrate the many ways in which the data process, from the very beginning of collecting data through filtering, annotating, using, in order to get your fancy AI system to work, is full of barriers and places to trip. I've tried to tell you some of the obvious stumbling points where your data collection and analysis can go wrong. But also, as you'll find from this question, there are also opportunities to do more analysis in natural experiments. And I hope you'll be able to take advantage of that. Thank you for sticking around a couple minutes later, but I appreciate it. And I'll see you all next week, okay?